University of Singapore. As we know, wireless sensor networks have been deployed in many applications of various environments. For example, we have deployed sensors on volcanoes, on Golden Gate Bridge, and in the forest. We have deployed sensors on the water surface of the reservoir. With all these applications, when the sensors are deployed, sometimes we may want to deliver a large bulk of data to every node in the networks. For example, we may want to change the code of every node, or we may want to modify the application profiles of every node. So we need a wireless data dissemination protocol. With this protocol, we can deliver the data from one source node to every node in the networks with wireless transmissions. Since we want to deliver some important information such as application profiles or updated codes, so we want the data dissemination protocols to be reliable. The reliability here means that we must guarantee that every node in the networks can receive the complete data object reliably. Of course, we want to do it as fast as we can to save the energy of the sensor nodes. In the last decades, the researchers in our community have developed many data dissemination protocols. Here, I just want to present some classic ones to try to show the technology progress. The first data dissemination protocol is proposed in 2004. It's called deluge. With deluge, the large bulk of data is divided into small pages. We transmit the page from one node to its neighbors using explicit acknowledge and the handshake mechanism to ensure the reliability. 3 years later, Sprinkler is proposed. With Sprinkler, a subset node is selected, as illustrated by the red nodes in the animation. With such a subset nodes, they form a backbone. They are responsible to deliver the data from the source to the rest nodes of the networks. 1 year later, rateless code is implemented for data disseminations. With rateless code, the original packet are first encoded into a stream of packets. Every encoded packet is a linear combine of some randomly selected original packet. So every encoded packet contains some novel information of the original data objects. Now, when we use rateless code to transmit a data in one hop, the receiver do not care about the ID of each individual packet. It only accumulates the enough number of packets. It will recover the data. Let's see an example. When the source transmits data packets to 3 receivers, at this moment, every receiver are missing one particular packet. However, instead of transmit one particular packet to each receiver one by one, the source only needs to transmit an encoded packet. Such one encoded packet will help all the receivers to recover the original data at the same time. So by using rateless code, the broadcast efficiency is highly improved within one hop. Later, until 2013, Splash is developed. With Splash, it is based on 2 techniques. First is constructive interference, and the second is pipelining. With these 2 techniques, Splash can build a fast pipelines. On the pipelines, as we can see, multiple nodes at the same layers in the tree topology can transmit at the same time without interference. And 2 different layers can operate at the same time too. So the data dissemination efficiency is highly improved. Now we are proposing Panda. It can further improve the performance of data dissemination and try to approach the network capacity. I will introduce later. Now, let's see the first technique. With the great work, glossy, now we can deliver a packet across the networks using constructive interference. Because the transmissions are triggered from one source, so the transmission of the multiple nodes at the same layer are highly synchronized. So when they transmit at the same time, the signals from multiple nodes interfere with each other constructively. By doing so, we can avoid the overhead of multiple access, such as CSMA or TDMA. Another technique is pipelining with the proper channel allocations. Now, we can enable two links works at the same time with different channels. By doing so, we can improve the spatial reuse of the networks. By combining constructive interference and pipelines, Splash built up a fast pipeline for data dissemination. As we see, multiple nodes at the same layers can transmit at the same time, and different layers can happen at the same time too. On this fast pipeline, every node is very busy. They are neither receiving packet from their parent or transmitting data to their children. So the data dissemination efficiency is significantly improved. However, it is just an ideal case. In reality, the fast pipeline is not so reliable. There are packet loss. So to handle this problem, Splash transmits the data, the original data, repeatedly in multiple rounds. As we see, even after several multiple rounds, there are still some nodes that are missing some packet. What Splash do is that it leverages a local recovery phase to achieve the 100% reliability of the networks. In the local recovery phase, every node asks for the missing packet from their neighbors using CSMA-based multiple access. Let's see the performance of Splash. We do the experiment on Indria with almost 100 of nodes. This is the y-axis is the reliability of the networks, and the x-axis is the dissemination time. As we see, Splash has a long tail problems. That is to say, it spends more than 80% of the total dissemination time to achieve less than 20% of the reliability. Why? We dig into the packet traces, and we found that in the second and the third round, there are more than 70% of the received packet are duplicate. And in the last local recovery phase, it is very time-consuming because it is based on CSMA multiple access. Now, we want to ask a question. Can we do it better? Can we accomplish the data dissemination process entirely over the fast pipeline? To answer this question, we propose Panda. It provides fountain-enabled data disseminations over the fast pipeline. Fountain code, just like rich list code, it inserts randomness to the original data. So when we transmit a fountain-encoded packet, the receiver does not care the ID of each individual packet. It just accumulates enough number of received packets. It will recover the data. Now, using fountain-enabled packets, data dissemination becomes very simple. As we see in this animation, the source just keep pumping into the networks the encoded packets, and every node in the networks relay the packet to the lower layers. And at the same time, they accumulate the correctly received packets. As long as they received enough number of packets, they will recover the original data. Okay, it is still an ideal case. In reality, we must tackle some practical challenges. The first one is we must accommodate the fountain codings in the fast pipeline. Let's first see what is fountain coding. To encode a data object, suppose we have a data object of n original packets. We use a coefficient metric to generate a stream of encoded packets. And we transmit this packet. The encoding complexity is big O m times n. And at the receiver side, when the receiver received n correct packet, it can recover the original data by using the corresponding coefficient metric. Normally, we use Gaussian elimination decoding algorithm. It contains two steps, triangulation and subword substitution. The computational complexity of Gaussian elimination is big O n cube. As we see, both encoding and decoding takes time. However, on the fast pipeline, every node is busy. They are receiving or transmitting. They have no time to decode. And we cannot stop the fast pipeline to decode because we want to accomplish the data dissemination process over the fast pipeline. If we stop there, we may find that there are some nodes are still missing packet. So we may resume the data dissemination again. So it's not efficient. So what we do is that we propose radio-driven coding scheme. To guarantee the constructive interference and pipelines, we need to guarantee the time synchronization. So the radio is very busy in such scenario. The radio are either in reception or transmission state, or it is transit from one state to another. What we found is that the microcontroller is not so busy, actually. It only has to do some important operations at some important time point. For example, at this moment, when the microcontroller receives an interrupt from the radio, it only needs to transmit some commands to the radio to trigger the transmissions of the radio. So after the transmission of these commands, actually the microcontroller has a long interval to be in idle mode. So we can leverage these idle intervals to do the decoding and encoding. By implementing such an idea on sensor modes with 802.15.4, we squeeze out more than 1,500 microseconds in each transmissions. Now, when the radio receives a packet, the microcontroller has 2 time slots to decode this packet. And when enough number of packets is received, actually the microcontroller can recover the original data at the same time when the radio is still working. To enable such an incremental decoding algorithm, we use our previous algorithm. It's called a cumulative Gaussian eliminations. It's proposed in our last paper, and you can find the details in the paper. Now, every node can recover the data where the pipeline is still working. The problem now is that the fast pipeline are one way. As we see, the data is flowed from the source to the leaf node continuously. So the relay node and the source node has no idea what is happening on the lower layers. So it cannot stop the transmission. However, when every node has finished the decoding, actually we can stop the data dissemination. So we need to find a stop condition. To do it, we propose silence-based feedback. Assuming we have a data object of 16 original packets, and every node needs 17 encoded packets to recover the data, the source first transmits the first packet to the first layer, and the node will relay the packet to the lower layers. and the source transmits the second packet, and 2 links happens at the same time, and so on and so forth, until the 17th packet is received by the first layer's node here at this moment. Okay? Actually, what we found is that instead of receive packet from the upper layers, the nodes at the first layer can generate the encoded packet by its own using the recovered original data. So instead of listening to its parents, this node can listen to its children. It can monitor the operations of its children. So at this moment, when the leaf node recovers the data, it stops transmission, such a silence of the channel can be detected by the upper layers by measuring the RSSI value of the channel. And if a silence of the channel is detected by the upper layers, it will stop transmission. Such a silence can be delivered to the source from layer to layer. Okay, to enable such a silence-based feedback scheme, we also need to handle some practical issues. First is the interrupt, is the interference. If there are some interference signals, the upper layers may detect the channel is busy, even the children has stopped the transmission. We call it a false negative of the channel silence. We solve this problem by adapt the RSI threshold of the channel silence according to the RSSI value of the last successfully received packet. So if there are interference, the RSSI value of the last successfully received packet will be high, so our threshold will be high to consider such a situation. Another problem is that the packet reception may be corrupted. So without a successful reception of a packet, the node cannot transmit in the next slots. Such a silence may be detected by the upper layers as a stop condition. So we solve this problem by stop the relay node only after 2 consecutive silent slots are detected. By using this method, we may improve some overhead. However, in our test, that 2 consecutive silence slot is very short because 1 transmission only takes several milliseconds. So the overhead is small. Now, every node in the networks can recover the data where the fast pipeline is working, and we can stop the fast pipeline as we have done the job. We have still one more challenge, is that we need to adapt the channel allocations. Let's see these experimental results. That we found the packet reception rate of different nodes are very different for each channels. For example, we use channel 26 as an example. The packet reception rate of channel 26 is very high at node 1 and node 2. However, its performance is almost 0 at node 3. So if the bad channel is allocated to some nodes, so this node's performance is very low. It may hinder the fast pipeline for a long time. For example, Splash changes the channel allocations in every round. However, in every round, we transmit the whole data. So it takes a long time. In such a long time, the per-performing nodes cannot receive anything. What we do is that we allocate, instead of allocating channels for each layer, we allocate channels for each packet. We use different colors to present channels. As we see, the packet is delivered forwarding to the leaf node, and it will not change the channel. However, the node can set up the channel accordingly beforehand by using the sequence number of the last received packets. By doing so, every node in the networks can experience all the available channels securely and equally. So the performance of the nodes are uniformly distributed in the networks. Okay, there will be less chance for one node that can handle the fast pipelines for a long time. Okay, that's the design of Panda. We implemented Panda on contiguity, with contiguity on sensor modes. This is a state machine of one node. We provide Panda as a middleware for data disseminations. So when a source wants to transmit a data object, it first transmits a Panda on command to every node. When received this node, receive this command, the node in the start state. We transmit data in pages just as deluge because of the limitations of the memory on sensor modes. And when we disseminate the data, every node are neither receiving data from the parent or transmitting data to the children or receive signals from the children as just what I have introduced. Here, I want to point out that we have some fault tolerance mechanisms. For example, if the packet is lost or corrupted, or the receptions of one packet is not complete, we have some mechanism to keep the nodes on the fast pipeline instead of drop off the pipeline. You can find the details in the paper. We evaluate the performance of Panda on 2 test beds. First is Flock Lab from ETH of Switzerland. The researchers there deploy almost 30 nodes in the indoor and outdoor environments. And another test bed is Indria from NUS Singapore. The researchers there deploy sensors, more than, I think, almost 100 sensors in an academic building. We compare the performance of Panda with Splash and Deluge. And for each approach, we run 5 experiments for different locations of the source node. By changing the source node, we change the network topology. Okay, for each test, we transmit a data object of 22 kilobytes. And for Deluge and Panda, one page contains 2 kilobytes data. This is the data dissemination results on Flock Lab for every node. As we see, when the bar becomes black, it means that that node achieves 100% reliability. As we see from the result, Splash needs almost 20 seconds to complete the data dissemination process. Panda only needs less than 7 seconds. And we achieve the same performance on Indria. Let's see some average performance. For the average performance is the average of the 5 tests for each approaches. And we can reduce the data dissemination time of Splash by more than 3 times. And on the Flock Lab, we can improve the performance of Splash by more than 6 times. And finally, we compare with Deluge. We run the contiguity Deluge on Flock Lab. It is a simplified version of original Deluge. And from the average result, we can see that Splash can improve the performance of contiguity Deluge by more than 200 times. And we can further improve the performance by 6 times. To conclude, in this work, we propose Panda. Panda is a fast data dissemination protocol for wireless sensor networks. Actually, Panda is a tree. It is the largest living organism on the Earth. As we see in this picture, you may see a forest. However, it is just one tree. All the branches on the ground is connected by one root underground. So we name our protocol as Panda because we want to propose data dissemination protocols that can connect all the sensors in the networks wirelessly. Now, when you use Panda to program the networks of hundreds of nodes, you can do it just like to program one node. Okay, thank you. I'm glad to take questions.